Right, now we're going to start looking at how we've touched on how we actually form things. But what I want to do is I now want to bring let me get my sodium and chlorine. Sodium and chlorine, I'm still using the same ones. We're going to look at how they form, because there's different types of bonds, right? Some bonds are stronger than others, right? And this is important to know because we've got to build up models that show us different kinds of material. Because why? Well, we've got different kinds of material, right? We've got salt, which is crystalline. We've got iron, which is a solid, and it's ductile. You can pull it and stretch it. It has tensile. Tensile is pulling strengths. We've got lead, which is a soft metal. Mercury is a metal, but for goodness sake, it's a liquid at room temperature. We've got air, which is a mixture of a whole pile of gases. Hydrogen, water, which can exist in different phases. So we need to go through and we need to understand how each and every one is formed. Why? Well, because in chemistry, we're going to, certain cases, break bonds. Let's take aluminium. Aluminium is in an ore called bauxite. We need the aluminium metal extracted from the bauxite, right? So we've got to find processes. That's what this is all about. It's leading us with a base understanding to find processes that we can extract these various metals and ores: iron, copper, zinc, silver, gold. There's different processes to extract the metals that we need. For example, liquid oxygen. Well, carbon dioxide, dry ice, how do we form it? These are all industrial processes driven by a demand that people have. Okay, so let's have a look. Before we do, if you look at your periodic table, okay, hopefully you've always got a periodic table close at hand, and please turn to a periodic table and have a look at it. I'm going to just take out, haven't got mine with me now, but if you just take out your periodic table and have a look at it, you will see that there's a number. If you look at fluorine, there's a number of 4.0 in the top corner over there. Chlorine has also, oxygen's got, all of them have got a number that is given there, right? This number is called the electronegativity. Electronegativity. And what does the electronegativity mean? Well, first of all, you can have a look. Some of them down on group 1, which is the group is the family 1, the lithium, the sodium, the potassium, the rubidium side, right? If you look down there, they've got low numbers. Fluorine is the highest, but if you look, fluorine, oxygen, chlorine, they're all relatively high relative to I use relative twice, but relative to the group 1. What does this number mean? Quite simply, electronegativity means, remember when we said that sodium has got 1 spare and chlorine, okay, let me just go back and just refresh. I'm only going to say sodium has got 1 spare and chlorine has got 1 vacancy, right? Remember what we said? Metals give, these take. Okay? Positive give, negative take. What it means is the chlorine takes the electron from the sodium. Sodium wants to get rid of it, chlorine wants to take it. That allows sodium to drop back, and if you look, it drops back to the same electron configuration as neon. It's a full up structure. Chlorine moves up to the same structure as argon, a full up structure, by taking this electron away. Now, sometimes the electrons are shared equally. Sometimes they are taken away completely. Sometimes the electrons are just sitting in a complete, let's say, cloud formation. We have to understand how this concept works. The electronegativity is the key to it, and it is called the Pauling scale. Okay? Pauling scale, Pauling scale. 4 being the highest. It means that this is the most electronegative element. It is the most electronegative element. Well, that tells us that fluorine is actually the element that is the greediest. The higher the number, the greedier that element is to take electrons away. The more it's going to take, okay? Or let me rephrase, the stronger the pull is going to be. So if you are dealing with fluorine, right, at 4, essentially any metallic element that comes into contact with fluorine is going to reach out and grab the electron from the sodium or the lithium or potassium, and it's going to take it away. So much so that that electron doesn't ever spin around its home element anymore. So what happens? The higher that number, the greedier. Let's have a look what happens if, for example, lithium and fluorine get together. Okay, fluorine is 4.0. Okay, now I don't have my periodic table here, unfortunately. Let me just have a look. There must be one in this book here at the back, usually. I just want to check for my periodic tables. Wished I knew where they always were, you know. It would help, wouldn't it? Okay. All my other books. Oh well. Okay. Not too serious. Don't worry about it. Chemistry. Here we go. It must be a periodic table. There we go. Okay. Right. We've got 4, and lithium is 1. 1.0. Okay. So what happens now? Right. Lithium comes along. Okay. I'll just keep this guy out. Lithium is number 3. Okay. So let's just have a look at the electron level. Just to explain it, conceptually, once you've seen it, you can do it for anyone. So lithium is element number 3. 3 protons, 3 electrons, right? Therefore, it's going to fill up the first orbital, 1s, level 1, 2, and it's going to have 1 electron. It's going to have in 2s1. We know it's a metal, therefore it wants to give. Now, the lithium comes along and the fluorine comes along. We know that fluorine was element number 9. So it's 1s2, 2s2, 2p5 to make 9. Now, I just want to do this diagrammatically, because like that. Okay, everybody happy with that except Kevin has put one in there which he shouldn't have. Okay, let's just okay, now remember it is there, so therefore we've got this one parking spot there. And remember, when this comes along and this electron over here, this one goes over and goes and sits in there, this became F minus 1, didn't it? Because it's got 1 extra electron more than the number of protons. This has got 9 protons, 10 electrons now, which means it is plus, or rather minus 1. It's got an extra minus charge, an extra negative charge. Okay. Now, so that's what we've got. But now what actually happens, right? What actually happens with this electron? Let us look at something here. Let us take the difference in electronegativity. Okay, so delta electronegativity is equal to 4 minus 1 is equal to 3. Right? That means that essentially the fluorine is so electronegative that the lithium and the fluorine join together, but the electron itself, okay, the electron itself is taken over there. This is plus 1 and this is a minus 1. So they are joined, yes, they are together as a couple, right? It's a single molecule of lithium fluoride, absolutely. But what has happened? What has happened is that the fluorine has taken the electron away completely. The lithium never sees that electron again. It's gone. Which means that this thing, right, this molecule that we've got here of lithium fluoride, or whichever way around you want to do it, let's take this as the green fluoride, lithium fluoride, like that, this process, it's taken the electron away. So this side is a minus 1 side. This side is a plus 1 side of the actual molecule itself, isn't it? Because the electron is permanently sitting on the other side. Now, so the difference in electronegativity tells us about the kind of molecule that we're forming, right? Obviously there's boundaries. Let's now talk about something just slightly different. If you go to your periodic table and you look, you've got nitrogen, oxygen. I'm already drawing it in what I want to say. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, chlorine, bromine, iodine. Can you see those over there? Can you see the shape that they form? It forms a 7, right? These here, okay, plus hydrogen are always together. They are H2, N2, O2, F2, Cl2. Okay, they're all gases. Br2 and I2. They are all gases, right? And they are what is called diatomic. Okay, 2 atoms. So, in order to make it more realistic, let me just get my, there we go. Here we are. There's chlorine, there's fluorine. They always exist together, joined with the 2 elements, the 2 atoms form together to form a molecule of those 2, and they're called diatomic gases. In other words, as elements, they always exist. As, let's say, Cl2 with a 2. Okay? When they are together with something else, you can have Hi, okay? Hydrogen iodide, hydriodic acid. But you can have them together like that in a compound. But on their own, as a gas, Cl2 gas, okay, they are always together. While we're talking about that, okay, we've got this little number, this little guy behind here. Let's just quickly go through those. We've got something as a gas, right? You can always have something as a liquid, okay, as a solid, and the last one is AQ, which is aqueous, okay. This means it is dissolved, okay. Essentially, usually in water, okay. Yes, we do dissolve things in various other things, in alcohols, ether, and so forth. But mostly, we're going to be dissolving in water. We're going to be looking at aqueous solutions, okay? So for that process, we've got these four: gaseous, liquid, solid, and aqueous. So when you see them behind in a chemical equation, you will see that they have got that little thingy behind them, okay? Usually, that is to indicate they're going to could change state. It can go from a gas to a liquid to a solid. Hold on. Hang on. Freezing point, melting point, boiling point, right? That's the phase change. So these here are indicating the phase of the substance, right? It's just telling us that we put a solid and add it to water, it then dissolves in the water. We're going to go through all of that as we sort of march through this chemistry of ours. Now, so that we don't get digressed, we've now got those that are diatomic gases. We're talking about electronegativity. The electronegativity is telling us what is essentially how powerfully one atom pulls the electron from another atom. Okay? Let's have a look. Nitrogen. All right? Nitrogen, we said, let's rather look at oxygen. It's just a little easier. Oxygen, all right? Remember we said oxygen on its own is O2. So let's pretend that this is oxygen now, our nice green lung gases. Oxygen, it comes together always with these two atoms to form a molecule. These two come along together, randomly bouncing around depending upon the temperature. Remember the velocity thing? Okay, randomly bouncing around. That is our oxygen molecule. There's two atoms of O. Two oxygen atoms form O2 gas. We don't find O in the atmosphere. We only find it occurring as O2, N2, H2, Cl2, Br2. So O2. Now how does it happen? Well, let's look at this. Oxygen is number 8. 8 protons, 8 electrons. Let's draw it. 1s2, 2s2, and 2p. That's 4. 4. So, okay. Let's do these. I know you're all okay with this now. All right. Like so, like so, like so. And just to recap, how many parking spaces? 2. Therefore, it's got a valency of -2. It's a nonmetal. It takes. Okay. Now, we said that oxygen, actually, let's draw it in green just for some fun. There's the oxygen, and we said that these two are actually stuck together. Okay. How? How do they stick together? Well, let's have a look. The oxygen has got electronegativity. Let's have a look at that. So this oxygen has got an electronegativity of 3.5. This one has got an electronegativity of 3.5, which means the change in electronegativity delta is 3.5 minus 3.5, which is 0. So there is no difference in electronegativity. They're equally electronegative, which means that the one oxygen doesn't take more of the electron time than the other one. So that means that they are going to be sharing. They are sharing. So let's have a look here. The oxygen and the oxygen are sharing. How do they do it? Well, another oxygen comes along. Let's put this oxygen in red, like this. Okay. Can you see? There he is. Maybe I shouldn't use red. Okay. And he has got, I'm going to just go to blue. He's got 2 parking spots as well. Whoa, hold on a second. These two actually physically get together and exist. So what happens? The only way that we can do this is this. I'm going to now have to go green. It means that this one and this one share with that one and that one. Doesn't it? So what is happening here is that we are sharing. Okay? We are sharing. And here's the rub. Equally the electrons. We are sharing the electrons equally. Right? What does that mean? That means that these electrons here, the ones marked in green, okay, the electrons come along and they say, oh, okay, remember, he's got 2 and he's got 2, right? So what do? Or she's got 2 and she's got 2. So they come along, here's the 2 spare and here's the 2. There's 2 parking spots. These 2 get together like that, right? These 2 come in and interlock like that. So this shares and this shares electrons with each other. That's what's happening here. They are taking their things and sharing it. So what have we got? We've actually got this. This one is sharing the electron here, and an electron here, and an electron. They are sharing the electrons. And because the electronegativity difference is 0, they are sharing it equally. So what is happening? Essentially, let's put in our, here's our atom, and here's our atom of oxygen. So that's an O, and that's an O, right? The electrons, this one, okay, is being shared. Can you see that? So the electrons, this electron is shared here, this electron is here. Remember, they stay far apart. So this one goes around, and this one goes around, and they shared equally. What does that mean? Simple. It means that no side of this is positive or negative, because there's always an electron here or here, right? There's not a positive or minus sign to this. Okay? It's pure sharing. Now, the last few words here is this, right? I need to go through and just quickly explain this process. Remember when we said lithium and fluorine? We looked at delta electronegativity, and it was high. And we said that we got a positive 1 and a negative 1 side of the lithium fluoride molecule, right? Remember that? What it means was that the electron is spinning around that side, right? The next one we got was an oxygen, okay? Delta electronegativity, in this case, was 0, okay? So there's no charge on the sides, which means the electron is doing this, okay? This is pure sharing. This one is no sharing, right? It's not shared at all. This here is called an ionic bond. Why? It's an ionic form. It is a negative and a positive side. The electron has gone. Essentially, we've got 2 ions together, haven't we? The ion is a charged atom, isn't it? We've got a lithium on the one side, which has got a +1, because all I've got is I've got my 2 protons and 1 electron over here. Rather, sorry, 2 electrons. I've got an excess of protons. This side, I've got an electron too many. So this is a -1 and this is a +1 side. That is an ionic bond. The pure sharing, okay, we call a covalent bond. Why? Well, let's just have a look at this. Just split it up. Covalent. The word valent comes from valency. Okay? Okay. Let's just put oxygen down again. Oxygen was number 8, right? Oxygen was 8. So we go 1s2, 2s2, 2p4. I'll just do this once again. Okay? And like this. Like so, like so, like so. There's 3 there. So we know we've got our 2. Now, this has got 2 parking spaces, non-metal, So it has a valency of -2. Non-metal, right? And how many parking spaces available for an electron? There's 2 spaces, so it's got a valency of -2. Now the difference is this. When we are looking to draw this using the next stage, the next section of work, we actually do this. We say, wait, hang on. The valent electrons are the outer shell. Outermost shell. Okay? What are we doing? We are sharing a valent electron. What do they say? Cohabit. You share the space, right? You cohabit a space, cohabit a country, cohabit a car. You're in it at the same time. You're sharing the space. Covalent, sharing, valent, valency electrons. We are sharing the valency electrons. We're going to, in the next one, we're going to be talking about the Lewis diagrams, the crosses and the dots and how these things fit together. We're going to do a few examples of that. So we're going to be going on and on a little bit more about this in the next section. Just always remember, have a periodic table when you're going through these. I should have said it right in the beginning, shouldn't I? But have it with you, because when we refer to it, you should be able to look at the numbers as I'm working through these, okay, and seeing this. Remember, we only draw the valent electrons, the outer shell electrons. That's all we're interested in. Why? Because these are the ones that take part in the bonding. The core electrons over here, these are called core electrons. This piece here. So, for example, if it was 1s2, 2s2, 2p6, 3s2, 3p5, right? These would be the electrons, and these would be core, and these here would be the valency electrons, the valent electrons. Okay. Remember, the difference we're going to have between valency is that number of parking spaces if it's a nonmetal, or the number of electrons that is going to give away if it's a metal. It's a plus a metal, a minus a nonmetal. Okay. I've gone over a bit there, but the next section, what we're going to do is we're going to look at putting some of these together by using the Lewis and the Lewis diagrams, the dot and the cross diagrams. Thanks for watching. I hope that's sort of cleared up some of the issues here, or if some of you are looking at this ahead of time, I hope it's giving you a great time when you're in the class, you've heard the terms, you've seen it gone through, so it's revision and it's allowing you to deepen your knowledge of this. Okay? Hopefully you're also seeing chemistry is incredibly logical. A lot of people don't think it is, but it really is. Thanks for watching, and see you in the next session.